Hello, this is Chris DeSalvatore, and in this tutorial, we're going to make a set of parallel plates, and we're going to calculate the Radks, which is the thermal radiation exchange factors, from them into space and between them. They're going to be identical parallel plates directly opposed to each other, and the length and width will be 10 by 5 inches, and the plates will be separated by 12 inches. We're going to define the lower plate as surface 1 and the upper plate as surface 2. So let's get started. First thing we need to do is go ahead into thermal. We go to optical properties and we go to edit property data. And we're going to define the first plate properties with white paint. So the new property to add box, we enter white paint. And we go ahead and hit add. Now, we're going to define the solar absorptivity, which is going to be 0.23 for white paint. And then we're going to change the infrared emissivity to 0.8 for white paint. And then we're going to OK out of there. That's all we're going to need for this example. And as you can see, it added white paint to the list with the values that we entered. So we know now that it is definitely in there, so we can OK out of that. So the next thing we should do is go to thermal and preferences and look at our units. In this case, we're defaulting all to metric. And in this example, we're going to be defining the model in inches. So we go to where model length is defined. We see that it is metric right now. So we hit the drop down menu and go ahead and hit inches and then hit OK. So now everything we enter will be in inches. So now we're going to construct the plates. So we would go into thermal, surfaces, solids, and rectangle. And once you become familiar with your icons, you can go directly to those commands at your icons. This is good for beginning thermal desktop users to navigate to where the commands are to use pull down menus. So anyway, we're going to start at the origin to construct our plates. So you can enter either at the cursor where you can see it highlighted, or the box at the bottom, the command line. So either way is going to work. So you can go ahead and type in 0 for X, hit a comma, goes to Y, hit 0 there. Okay, so now it is asking to the plus X axis, which is going to give us our length. So we're going to go ahead and hit 10, comma 0. That gives us our length. And now it's asking for the XY plane, which gives us our Y direction, which is going to be 0, comma 5. So now we have our first plate constructed, and it is now asking us for properties. So here we're going to go into the radiation tab, and we go ahead and select base both here and hit edit. And we're going to have to go and put top out, since this is the bottom plate, and hit OK there. And over here in optical properties for surface radiation calculations, we're going to need to define the top as white paint. And we're going to go ahead and define the bottom as white paint too, because later on we're going to be copying this directly above it. So we can take care of the white paint properties here by doing that. So we can go ahead and hit OK. So now we have that defined. Now you can see that it's put a node in the center of the plate. So if we want to have that node there, it's fine if we don't have a very cluttered model. But oftentimes it's good to go into the thermal references and go to the graphics visibility tab. And it's got global show options here. So the TDRC node that's there, we can unselect that and hit OK. You can see that it's taken away the node. So with more complex models, this will reduce the clutter and make your visibility a little bit better. So we're going to go ahead and make the next plate. So I can go into modify and copy. And I can go ahead and hit my rectangle here. And then I go ahead and hit enter. And now it's asking me for my displacement to copy. And since this is going to be 12 inches above in the Z direction, I can go ahead and hit 0, 0, 12. And that's going to give us the rectangle defined. We need to hit enter here for it to complete the command. And you can see that it's entered the second plate at 12 inches above. So at this point, we go ahead into thermal edit and we select the top plate. And we want to select base top here and edit. Now, since this is the top plate and it's going to be talking to the plate below it, we're going to have to change this to bottom in so that they're now looking at each other, and hit OK there. And we go into the numbering tab. First one had defaulted to 1, which is where it's going to default unless you change it. So, but since this is going to be our second plate, we're going to want to identify it as 2 here. Then we hit OK. So now they're distinguished from each other. Okay, so now we go into thermal and we do model checks. You go active display preferences. And now we'll want to, in this case, go ahead and display with arrows so that it shows that they're both looking at each other. So I'll go ahead and hit OK here. And what I could have done there, I mean, there's another way to do this, but they've, in this version of Thermal Desktop, they've updated it so you can do it right there. I'll go back into Thermal Model Checks. Activate display preferences. Now I had put arrows, and you can go ahead and hit display over here, and it shows, yes, we're successfully having the plates look at each other. So the next thing we need to do is go into thermal radiation calculations and set radiation analysis data. And we go into the control tab. Well, we're defaulted to the control tab handily there. And we're going to define the rays per node. And since this is just an example, not really a direct application of this, but just to test the capabilities of the program, we'll put a bunch of nodes there just to see what happens. We got 100,000 that we'll put in and see how the program deals with that. So next we go into the advanced control tab and we deselect use octree to accelerate calculations because that's for much more complicated models, and we've got a fairly direct, simple model here, so we're not going to need to have that capability in this particular example. So next we'll look at the Radk output tab, and we're looking at the list summary if percent kept is off by more than line. We've got 10 defaulted, but we only really need to have 0 there because this is not particularly complicated. So we don't need to worry about that. So go ahead and hit OK. So now we go to thermal radiation calculations and calc Radk's ray trace. Okay, so this is going to do our calculation. It's asking us, are we all set? Are you ready to run? And yes, we are. So we're going to hit OK here. All right. So now this is asking us, we've created a new database and do we want to keep it? And yes, we do. We're going to go ahead and do that. All right. So what's been done here is that the results have been put into a file in the folder, the working directory where you opened your model. And so we're going to look for the cinda.k file. I'll pull that up here. I'll jump ahead with the file so we can just carry on directly from there. Okay, so I've opened up my cinda.k file and I can go through and explain this a little bit here. At the top, we got some basic information telling us when it was created and all, and we got our some of our input data, the cutoff factor, and the conductor units are in inches squared. After it says p-stop, right below that, it shows the thermal properties that we had entered and the files that they generated from which we drew the property data. The thermal physical property database is the tdthermo.tdp file, and the optical property database is the rcoptics.rco. And these are files that you're going to need in your working directory in order to run thermal desktops. So you always want to make sure you've got those two in there before you start. Okay, so next down we got optical properties used, and since we only entered emissivity and absorptivity, those are the two that are listed there, and it shows the property name, white paint, and you can see those two values there. And below that, we've got the RADK format. And as we mentioned earlier, there's three different scenarios shown here from main one, which is the bottom plate into space. And the used area there is shown. And then some of the output data. And then the second line is main two to space, which would be the second plate. And line three would be main one to main two, which is the plates talking to each other. And in the bottom summary section here, we've got some of the input data shown, main one being the bottom plate. It's showing us the 50 square inches there. The number of rays that we shot being 100,000 in this case, roughly. Looks like there's a little bit extra on the main one there. You can do that sometimes. And our emissivity values and some of the data from the run is shown there. So that is essentially what we've got in the cinda.k output file. Okay. So at this point, we can go ahead and select thermal radiation calculations, set radiation analysis data. And we can go to the control tab. And we're going to prepare to plot here. And since in this run, we did 100,000, which would be pretty cluttered graphics if we try to do that. So what we're going to do was we're just going to set that back to 20. So it'll be a little more appealing to look at. And we're just going to look at the rays from the bottom plate. So we can go down here in the nodes and just hit list. And then just say main one, main.1, and that defines the bottom plate. And instead of everything, which would we would be given if we picked all, we're going to list just what we want. And we got main one, the bottom plate shown there. So if I hit OK and go into plot rays from surface to surface, which is the ray plot tab, thermal radiation calculations. So we go to the ray plot tab here. We want to look at the rays going to space. And we're going to want to look at the rays going from surface to surface. And we're going to want to go maximum number of rays 12, so we're not cluttering up the drawing too much. And we type OK. And now we go to the scale, LT scale. We're going to set that to 0.5. This sets the scale for our lines, defining our segments on our surfaces. And if it's going to be a much larger piece of geometry, then we go with a bigger value, but 0.5 will be fine for this particular geometry. So now we go into thermal radiation calculations and calculate Radks to ray trace. And it's asking us, do we want to continue? Are you sure you want to do this? So you're all set, and you say yes and hit OK. And now the graphics, as you can see, display all of our rays into space and between the plates. So there's several orange lines here representing the rays. So the rays are random, and they'll be different every time the calculations are made. And the colors of the rays are a function of the energy of the ray. Energy values of 1 are red and scale down to dark blue from 0 values. The color will change as energy is absorbed and the ray is reflected. So that's the graphic results. And in the syndicate file, we got our data as a result of the input to this particular problem. So at this point, if you want to get rid of your results on the screen graphically, just go ahead and go into thermal radiation calculations and clear ray plot. Plot's cleared. And that is how we do the RADK calculation to determine the thermal radiation exchange factors between two plates and off into space. So I hope you enjoyed that and you got something out of it.